Hello students, this is lecture 13 and the content of our today's lecture is we are discussing about the gamma distribution. Today we will discuss additive property of gamma distribution. We will also see its generalized version, generalized property. We will also discuss some results, standard results about the gamma distribution, and in the last we will solve some examples of gamma distribution. So let's start the session. Well, we will discuss about additive property. Its statement is if x follows gamma distribution with parameter hmm, alpha comma lambda 1, y follows gamma distribution with parameter alpha lambda 2, x and y are independent, then x plus y follows gamma distribution with parameter alpha uh, comma lambda 1 plus lambda. Let's see its proof. Let x follows gamma distribution with parameter alpha comma lambda 1. Then its MGF is 1 minus t upon alpha is to minus lambda 1. Also, y is gamma alpha comma lambda 2. MGF is 1 minus t upon alpha. You have to find out the distribution of x plus y. So consider MGF of x plus y is given that x and y are independent. So by the property of MGF, if x and y are independent, then MGF of x plus y is nothing but mx. Just put the values of mxt and myt here. We will get this 1 minus t upon alpha is to minus lambda 1 plus lambda, which is the MGF of gamma distribution. Is MGF of gamma distribution with parameter alpha lambda 1 plus lambda. Therefore, by uniqueness property of MGF, of MGF x plus y follows gamma distribution with parameter alpha comma lambda. Now let's see its generalized version, that generalization. So we can generalize this result that if xi follows IID, not IID, independent, these are independent random variables with parameter gamma random variables with parameter alpha and lambda. Summation xi follows gamma distribution with parameter alpha is fixed, lambda 1 plus lambda 2 plus That is summation xi follows gamma alpha comma summation lambda I. That's it. This is the generalized property of additive property of gamma distribution. Now we will discuss some results. Standard results for the gamma distribution. So first is if x follows gamma distribution with parameter alpha comma lambda, then alpha into x, or you can take the constant c into x. This follows gamma. This c comes to be divided here alpha upon c lambda. Proof is very simple. We will prove this by MJF approach. So if x is gamma alpha lambda, its MJF is 1 minus c upon alpha consider, we have to find out the distribution of Cx. So consider MGF of sub t, which is nothing but mx of Ct equals to 1 minus, replace this t by Ct, one minus t upon. So which is the MGF of gamma distribution with parameter which is GF of gamma distribution with parameter alpha is alpha upon c here now. This is therefore by uniqueness property of MGF alpha, sorry, constant c to x. This follows gamma distribution with parameter alpha on c. Now next result, that if xi's are independent gamma variate, with alpha comma lambda I, then x bar follows gamma distribution with parameter n alpha summation lambda I. Okay, its proof is very simple. What is given? Xi follows independent gamma variate with parameter alpha comma lambda I, and just above we prove that by the additive property summation xi follows gamma distribution with parameter alpha summation lambda I by additive property, generalized additive property. By additive. So now if you divide this summation xi by n, this will be follows gamma. Now just we have seen one result, that if x follows gamma alpha lambda, then cx follows gamma alpha upon c lambda. So summation xi upon n follows gamma. This is divided by n, so multiply it by n here. What we prove here, if x follows, what we use here, if x follows gamma alpha lambda, Just above result. Then follows gamma t. This way, summation xi upon n, which is nothing but x bar, follows gamma, then alpha summation lambda. In this way, we can prove this. Now, next result. If x1 and x2 are independent, IID exponential variate with mean, that is if xi IID exponential rates with mean 1 upon alpha. It means with mean upon alpha means parameter alpha. Then summation xi, that is x1 plus x2. Same x1 plus x2 follows gamma distribution with parameter alpha comma. As in the earlier lectures of exponential distribution, we have discussed that additive property is not satisfied for exponential distribution if x1 and x2 are independent exponential variate. But students, if they are identical also, it means if xi's are IID, then its additive property holds, but it does not satisfy exponential, it will be gamma distribution. Okay. Proof is very simple. We will prove this by the MJP approach. Its MJP is 1 minus t upon alpha minus 1 for I is equals to 1 comma 2. We have to find out the distribution of x1 plus x2. So consider MJP of x1 plus x2, but MJP of x1 because if x1 and x2 are independent, then by property of MGF of x1 plus x2 is nothing but mx of t into mx2 of t. Just plug the values. MJP is 1 minus t upon alpha. Will be 1 minus t upon alpha. 2. Therefore, x1 plus x2 follows gamma parameter alpha comma. This way we can prove. Now next result. Can generalize this property. We have proved in the result 3 or 2 variates only. Can generalize it. Xi follows IID exponential distribution with then summation xi I equals to 1 to n follows gamma distribution with parameter alpha comma. The proof is very similar as of result. Do this proof your own, very similar. Thus instead of x1 plus x2 you have to do this for summation xi. That's it. Now the next result. Next result also we will just provide statement. Result is if x is standard normal, then its square is chi-square 1, but gamma by 2 comma. These are the results about gamma distribution. Now we will solve some examples on gamma distribution. Suppose x1, x2, x3, x1 follows gamma 4 comma 2, x2 follows gamma 4 comma 4, comma 3, and x follows gamma 4 comma 1. All are xi's independent. I equals to 1 are independent respectively, independent, and z is equals to x1 plus x2 x4. The question is, first is identify probability distribution of z. Second, find expectation of z and variance of z. So if you observe each xi, x1, x2, x3, x4, the alpha is fixed, lambda is varies. So you can apply by additive property. By additive property, z is equals to x1 plus x2 plus x3 plus x4. That will be follows gamma alpha, that is 4 is fixed, lambda 1, that is 2 plus 4 plus this will be gamma 4 comma. Which property we have used here? Is if xi independent, gamma alpha comma lambda I, then additive property xi gamma fix mission lambda. This is the first part. Second, expectation of z. So if x follows gamma alpha lambda, then the expectation of x is lambda upon alpha. Variance is lambda upon alpha square. Lambda is 10 on 4. Variance is lambda upon square upon 60. That's it. You can solve this. 0.62. Let's see some more examples. Let x1 follows gamma 6 comma 3 follows gamma 9 comma 4 follows gamma 3 comma 2. All are independent. Then first identify the distribution of identify the distribution of z, which is equals to 2x1 plus 3x2 x3. Can find of z sub z. The one is state the values of first four central. Okay. Now x1 follows gamma 6 comma 3. We have to find out the distribution of 2 times x1. So 2 times x1 will be gamma 6 upon 2, which is nothing but 2x1 follows gamma. Which property we used here? That is, if x follows gamma alpha lambda, then c into x follows gamma alpha upon c lambda. Similarly, now x2 follows gamma 9 comma 4. So 3x2 follows gamma 9 upon 3, that is 3 by 4. Similarly, x3 follows gamma 3 comma 2. Okay. Now by additive property, since this x1, x2, x3 are independent, two x1, 3x2 and x3, they are also independent. Are also independent. Therefore, by additive property, additive property 2x1 plus 3x2 plus x3. ठीक आहे, याला काय म्हटलेलं आहे? तर z म्हटलेलं आहे. This follows gamma alpha is fixed here. Now we can observe या ठिकाणी alpha 3 आहे, या ठिकाणी 3, या ठिकाणी 3. Lambda 1 is 3, lambda 2 is 4, lambda 3 is 2. 3 plus 4 plus 4 7, 7 plus 2 is 9. So the distribution is काय होता? is 3. Lambda 1 plus lambda 2 plus lambda 3. Second expectation z is lambda upon alpha by 3 sub z lambda upon alpha square alpha. This square is 9, so upon 9. That's it. This way we can find out the mean and variance. Then the values of mu1 is always 0, mu2 is variance lambda upon alpha square, We have just computed. Mu3 is 2 lambda upon alpha cube. If you put the values, you will get 2 by 3. And mu4 is equals to 6 lambda 3 times lambda square divided by alpha raised to. Just plug the values. All this will get the answer by. Next example. Suppose MGF is given to you, mx of t minus 3t is to minus 12. T is less than 1 by 10. Identify the distribution. Identify distribution. Find mean and mode. Find beta 1 and beta 2. So students, you can easily compare this given MGF with the MGF of gamma distribution is 1 minus t upon alpha minus lambda one minus 3t raised to minus 12. You can convert this into above form is 1 minus t upon 1 by 3 raised to minus 12. So if you compare, you will get y is equal to 1 by 3, lambda is equals to. Therefore, here x follows gamma distribution, parameter by 3, and so mean and secondly, mean is lambda upon alpha. Lambda is 12. To solve this, you will get this is 36. And mode is lambda minus 1 upon alpha. This is 11 on 1 by 3. Okay. At last, third one, beta 1 is 4 upon lambda. Plug the values, solve it. Lambda is 12, you will get 1 upon 3. And beta 2 is, formula is 3 plus 6 upon lambda. 3 plus 0.5, 3.5. That's it. So this way we have to solve the example based on gamma distribution. That's it. For today's lecture, we stop here. Students, this gamma distribution, exponential and gamma distribution is also over here. From the next lecture, we will start the next chapter, sampling distribution. That's it. So for today, stop here. Thank you.